Hey students, welcome to lecture number 4 of Linear Algebra 1. So last time we talked about functions from a set x to a set y, and then we introduced some properties for functions, which were injective, surjective, bijective. And today we want to talk about special functions which play an important role in linear algebra and which are called linear maps. So the functions we are interested in are going from the set Rn to the set Rm, and they preserve some algebraic structure in these two sets. So what do I mean by this? So we learned that here in the set Rn, so these are the vectors of size n. So if I take two elements out of this set, u and v, then for example I could add these two elements, u plus v, which just meant that I add the entries component-wise. And this again gave a vector of size n. And also if I have some real number lambda, which is called a scalar, we had this scalar multiplication where I multiply a number with a vector, and this also gives a vector again. And this just meant we multiply each entry with lambda. But the same we can also do in Rm. If we take a vector of size m, we can add two vectors of size m, and we can also multiply it with a scalar. And the linear map, if f is the linear map, then this means that it behaves well with respect to these two operations. So this means if I take u plus v, so again this is in Rn, then I can apply this map f, because it maps from Rn to Rm, and this here is now a vector in Rm, and if f is a linear map, then this means this is the same as first mapping u to Rm, so this here is in Rm, and then add f of v, which is also in Rm. And the statement then is, if f is a linear map, then this is the same. So here this plus is a different plus than this plus, because this plus here is between two vectors in Rn, and this plus is between two vectors in Rm. So this will be the first condition for f to be a linear map, and the second condition will have to do with the scalar multiplication. So the scalar multiplication also makes sense in these two sets. So if I take the scalar multiplication of lambda with u, so this is a vector in Rn, so I can apply this map f. So this here will be again a vector in Rm. And then the statement is, this is the same as first applying f to u. So this is a vector in Rm. And then multiply in Rm with the scalar lambda. And this will be the second condition for this map f. And of course these two conditions are not satisfied by arbitrary maps. And in the homework and in the tutorial, and also today, we will see some examples of functions from Rn to Rm which are not linear maps, but we will also of course discuss functions which are linear maps. Okay, so let's start. So here is just again the definition. So a function from Rn to Rm is called a linear map if for all, so here are three, this needs to be satisfied for all vectors uv in Rn and any real number lambda, we have these two conditions, that f of the sum of two vectors is the same as first taking the map f of these two vectors and then later add them in Rm. And the second condition is with respect to the scalar multiplication, that if I multiply a scalar with a vector u and then apply f, this is the same as first applying f to this vector u and then multiply it with a scalar in Rm. And just a remark, so in linear algebra 2, we will generalize this concept a little bit more. We will replace these Rn and Rm by so-called vector spaces, which are a more general notion of spaces. So there we will consider maps v to w, where v and w are so-called vector spaces. And the definition of a vector space is just that this is some set where you have some addition and some scalar multiplication. So there exists some addition and some scalar multiplication. And then the definition of a linear map between two vector spaces is exactly the same. And then here this plus will be the plus in V, and this plus will be the plus in W, and similar for the scalar multiplication. But this is just a comment. So for example, one example for a vector space which is not Rn or Rm would be, for example, the space of polynomials. So if I have a polynomial, or if I have two polynomials, then I can add these two polynomials and get a new polynomial. And also every polynomial I can multiply by a number. So this would be one example of a vector space. And then you can talk about linear maps between the spaces of polynomials. But in linear algebra 1, we will just focus on the space of Rn and Rm. And actually in linear algebra 2, we will also learn that this is the most important case because if we talk, for example, of the polynomials of degree 10, then we can actually identify this vector space with R11, where these 11 numbers correspond to the coefficients of these polynomials. Okay, so let's do an example. What is an example of a linear map? Well, actually, we already saw a lot of examples last time. So if I have a matrix, an m by n matrix, then, so we fix this matrix A, then we can define this map f, or this function f, from Rn to Rm by saying we send a vector just to A times this vector. Here, if this vector x is a vector of size n, then if I multiply it with an m by n matrix, then this here will be a vector of size m. And the statement is that this is a linear map. And why? Well, we need to check that we have these two conditions. So maybe let me steal the definition here. So we need to check that these conditions are satisfied for all u and v and for all lambda. So for the first condition, what is f of u plus v? So now assume u and v are in Rn and lambda in R. So what is f of u plus v by this definition here, where this means I multiply a to the vector a u plus v. And now you showed in the homework, or we saw in proposition, so this is proposition, I think 2.4. Yes, proposition 2.4. That if I multiply a matrix to the sum of two vectors, this is the same as multiplying the matrix to the first vector plus multiplying it to the second vector. And this is what you showed in homework 2, exercise 1. But then this here, this a times u is exactly the definition of f of u plus, and this is the definition of f of v. So we see, because this proposition here holds for any u and v, we see that f of u plus v is the same as f of u plus f of v. And therefore, the first condition here is satisfied. And for the second condition, it's quite similar. So we want to see what is f of lambda times u. Well, by definition, this is a times lambda u. This is how this f is defined. And again, by proposition 2.4, you showed that if I have a matrix and I multiply it with lambda times a vector, then the scalar can just go in front, and you can multiply lambda with the vector au. But this is again lambda times. So sometimes I will write multiplication here or not, but it's exactly the same. So this is the same. Au is the definition of f of u. And you see that we have the second condition. So therefore, every time we have a matrix, we can construct a linear map. So any matrix of size m times n will give a map from Rn to Rm. Okay, so but now let's do a function let's consider a function which is not a linear map. So let's, for example, the function, let's go from R2 to R2. So I need to send a vector of size 2. Let's call it x1, x2. I will send to the vector of size 2 where I take here as the first entry x1 times x2, and the second entry is just x2 or x1. And the statement is this function is not linear. Why? So now, to show that something is not linear, we need to show that this condition here does not hold for all u and v. So it's enough to just show one counterexample. So we just need to pick one explicit u and v such that this condition or this condition is not satisfied. So we don't need to show that it's not satisfied for all u and v. It's just we need to show one counterexample in order to see that this map here is not linear. And for example, in this case, we could, for example, choose lambda 2 and u11. So I want to show that the second condition here is not satisfied. So I want to show that for this lambda and u, this is actually not the same. So let's see, what is f? Oops. So I use a small f here. So what is f of lambda u, where this is f of 2 times the vector 1, 1, and 2 times the vector 1, 1 is just the vector 2, 2. And here again, as I said last time, if I have a function from vectors, from vectors to some space, I usually don't write these additional things here, so I can just write f22. And what is f22? So now we need to use a definition here. f22 means I multiply 2 and 2, so it's 4, and here it's 2. And but what would be lambda times f of u? So this would be 2 times f of 1, 1, 2 times, and now we need to evaluate f of u first. So what is f of 1, 1? It would be 1 times 1 and 1. So this is 1, 1. And now if I multiply at the end with this 2, this will give 2, 2. But now we see that this is not the same as this. So this is not the same. And therefore f of lambda u is not the same as lambda times f of u in this one special case. So maybe yeah. And therefore, f is not linear. And I cannot say it enough. It's enough to just give one counterexample. Often students in the homework try to disprove both conditions, but the definition of a linear map is that it really needs to satisfy this condition for all u and v. And therefore, if there's just one single counterexample for one of them, even if the other is satisfied for all, then it's enough to show that this is not a linear map. So here we are done, and this single counterexample shows that this is not a linear map. Okay, so now we have an example of something which is a linear map, which looks like this, and an example of something which is not a linear map. And the main statement is actually that every linear map looks exactly like this. So if I have a linear map, then I will always find a matrix A such that this linear map can be actually written as A times X. So this will be the first theorem today. So the statement is, if I have, so let F be a linear map from Rn to Rm, then there exists a unique matrix which we denote by this. So we use the same name as the map f, and we put it in these square brackets. And this is now a matrix, an m times n matrix. And then the statement is that this f of some vector x is given by multiplying this matrix f with this vector x. And this matrix, so this is a definition, so before we give the proof, just the naming, this matrix of this linear map f is just called the matrix of f. And here it's really important to understand what this means. So this here, the left hand side, so this is the evaluation of the map f at this element x. Of the function or map. At x. And the right hand side is something different. Here this is a matrix and this is a vector. So here we multiply, so this is a multiplication of the matrix square bracket f with x. I mean, both of them give something in Rm, because this is an m times n matrix and x is a vector of size n. So this gives something in Rm, and also this gives something in Rm because f is a function from Rn to Rm. So if I evaluate it at something, then the output will be something in Rm. And the statement is this is the same. So in other words, the statement of this theorem is that every linear map has this shape here. And in this case here, this matrix A is exactly the matrix of this linear map F here. So here we could say that this A in this example is the linear map as the matrix of the linear map F. Okay, but now let's prove this. How can we actually, if I give you some linear map, how can you actually construct this map as this matrix F? So for this we will first introduce some notation. So if I have a number between 1 and n, we define the unit vectors, which we denote by ej. So this will be a vector of size n, and this j is now a number between 1 and n, and this just means that everything here in this vector is 0, except at the place, at the row j, we have a 1. So here everything is 0, but at one place there's a 1, and the rest is 0. And this position of the 1 is just j. Okay, and these will appear several times in the lecture, so it's really important to remember this notation ej here. So if we have a fixed n, then ej just means we have n different ej's, and e1 has a 1 here, e2 has a 1 there, and so on. And with this, what we can do is, so then if I take a vector x of size n with entries x1, x2 up to xn, can be written as, so the statement is that I can write x as x1 times e1 plus x2 times e2 up to xn en. And what is this multiplication here? Well, this xn is this entry, this x1 here is this entry here, so this is a real number. So this here is a scalar multiplication. So this here, scalar multiplication. So what this means if I multiply E1, which has a 1 here and the rest is 0, with the number x1, this just gives a vector which has x1 in the first place and the rest is 0. This guy here is, it has just x2 in the second place and the rest is 0. And here this one, for example, is everything 0, except in the last place we have xn. And by this it's clear that this vector x here can be written as a sum of these n vectors, because the first entry of this vector just gets this x1 here and the rest doesn't give anything. The second entry comes from here and so on. Okay, so now we want to apply f, our linear map f here, to this vector x. So we can apply it to this sum here. So f of x equals f of, well, now we can write down the sum here, x1, e1, x2, e2, xn, en. And now what we can do is, well, f is linear, so here we use now f is linear. So it's a linear map. And the one condition of being linear means that if I have a sum of two vectors, then I can write it as f of the first vector plus f of the second vector. So for example, I could say this here is u, and for example the rest here is v. Then here I consider f of u plus v. So this is the same as f of u. So in other words, this is f of x1, e1 plus f of x2, e2, xn, en. So here this is f of u and f of v. But now the same I can do here. So f is linear, therefore I can write it as this plus the rest, and I can split it up and say this is f of this plus f of this. And then here in the rest I can also split up the first and say it's f of this plus f of this. So after a few steps I see that this I can write as a sum, f of x1 e1 plus f of x2 e2 plus f of xn en. And so here we use the first condition of being linear, but we also have the second condition where we know that if we have a scalar multiplication, lambda times a vector, we can put the lambda in front. But here we also now have, so this x1 is a scalar, it's a number, so here we have lambda and u, and because f is linear, we can put this lambda in front. So this here is x1 times f of e1. And the same I can do here, I can put the x2 in front. So here we use number 1, and maybe here we use the condition 2, that this is x1 times f e1 plus x2 f e2 plus xn f en. Okay, so finally the value of f at some arbitrary vector x with entries x1 up to xn can be written as x1 times f of e1 plus x2 f of e2 up to xn f of en. And this already shows that if I know the values of a linear map at these special vectors, these ej's, then I know the value of f at any vector, because I just need to use this formula here and write the entries of the vector in front of these values of f at these e's. But now how do we construct the matrix we are looking for? So we want to construct this matrix of f, this square bracket f, And so this we will do now. So we define the matrix of F by now considering the matrix which has these values as its columns. So here I put Fe1. So Fe1 is a vector of size m. So this here will be really a matrix with m rows. And this is the first column is given by the value of f at e1. The second column we use the value of f of e2 up to f of en. So here the size of this, the number of columns, is n. So this is really a m by n matrix. And the statement now is that this is exactly the matrix we are looking for. So f of x should be the same as multiplying this matrix with the vector x. But what is? So what happens if we multiply this matrix with the vector x? So in other words, we take this matrix F and we multiply it with x1, x2 up to xn. Well, so what happens if we multiply a vector with a matrix? So for example, if I have the matrix A, B, C, D, and I multiply it with x1, x2, what is the definition of this? This would be x1a plus x2b, x1c plus x2d, and this I can also write as x1 times ac plus x2 times bd. And you see here, so the product of this matrix with these vectors with entries x1 and x2 is exactly given by taking the first entry here times the first column of A plus x2 times the second column of this matrix. So these are the columns of A, B, C, D. But this works in general. So if I take a matrix with this vector here, then what I get is exactly x1 times the first column of this matrix, and the first column of this matrix is this vector Fe1. So this gives x1 Fe1 plus x2 times the second column Fe2 up to xn times the last column Fen. So therefore the product of this matrix with an arbitrary vector with entries x1 to xn is given by this sum here. But this sum is the same as we had before. So, well, it's exactly the same sum, and therefore this product of this matrix is the same as evaluating our linear map F as this vector x. So therefore, f of x equals the multiplication of this matrix F with the vector x. And the matrix F is just given by the matrix where we write the values of our map at the special vectors e1, e2 up to en as columns. Okay, so let's do an example for this. So also here the statement that there's a unique matrix follows, because there's just one way we can write x in terms of these e1 up to en. So anyway, so the proof is finished here, so we can make a square here. And now let's do an example of a linear map and the corresponding matrix. So for example, if F is a map from R2 to R2, with the following properties. So I say F is a linear map, and F satisfies that if I apply F to the vector 1, 0, so recall this is E1, is, for example, 1, 2, and I give you the information that f of 0, 1 equals 3, 4, then I could ask you, what is the value of f of minus 1, 3? So for an arbitrary map, if I just give you the value of this arbitrary map at 2 points, then of course you wouldn't be able to calculate the value of this map at some other point. But because f is linear, and I give you the value of f at e1 and here at e2, this is already enough to know the value of f at any point. So for example, if I want to calculate the value of f at minus 1, 3, then because minus 1, 3 can be written as minus 1 times 1, 0 plus 3 times 0, 1, and because f is linear, this means this is minus 1 times f 1, 0 plus 3 times f 0, 1. You can evaluate this. So now we just need to look up what is f of 1, 0. It's 1, 2. So this is minus 1, 2 plus 3 times f of 0, 1. So this is 3, 4. And therefore, so here this is 9 and 12. So minus 1 plus 9 is 8. And minus 2 plus 12 is 10. So the value of this linear map at the vector minus 1, 3 is 8, 10. And in general, what is f of x1, x2? Well, by the theorem before, we learned that the value of f is given by the matrix of f times the vector x1, x2. And what is the vector of x? The vector of f? The matrix of f, sorry. The matrix of f was given by the matrix where the first entry is given by the value of e1 and the second column is given by the value of f of 0, 1. And in this case, this here is 1, 2. So this is the matrix 1, 2 with the first column. And this is 3, 4. So the second column is 3, 4. And we can multiply it by x1, x2. And this here is the matrix of f. So in this case, we could multiply it out and see the value is given by x1 plus 3 times x2, 2 times x1 plus 4 times x2. So therefore, you can evaluate f at any vector x by this explicit formula here. And you can check if you plug in minus 1 and 3 that you get exactly this 8, 10. Okay, so this is really nice. So again, if I have a linear map and I know the value of this linear map at these just, in this case, 2 vectors, then I know it for all other vectors in R2. But this works in general, so this here is example 1, because this idea here, if I know, for example, the value of f at some other vectors, at 2 other vectors, such that I can write any other vector as some combination of these 2, like here, then I would also know the value of f at an arbitrary place. So let me do this more precisely. So this works more in general. So now let's consider, let's say f is a linear map from R2 to R3. But now I say, I give you the value at 1, 1, and I say the value at this vector of size 2 gives this vector of size 3, 0, 1, 2, and I give you the value at 1, 0, which is 1, 1, minus 1. And then I can ask you, what is the value at an arbitrary other point, x1, x2, x3? Oh, sorry, this is a vector of size. So what is the value of x1, x2? So now I give you the value of f not just at these e's. Well, this is e1, but this is not e1. But the statement is that you still can figure out what the value of this f at any other point is. So maybe you can try by yourself and stop the video and try to figure out what this here is, given this information here. So how to do this? Well, we see that if I take any vector, then I can actually write it also as a combination of these two vectors. In this case, it's a little bit more complicated. So in the theorem, it was really easy to see how to write any vector in terms of these e1, e2, and so on. Because for e1, I just took the x1. For e2, as a coefficients, I took x2. But still, I can write any vector as a combination of these two. And this, you can check that this works, for example, by taking x2 times 1, 1 plus x1 minus x2, 1, 0. Because what is the first entry here? So here I get an x2, and here I get x1 minus x2. And therefore, if I add this, I get x1. And here, well, here the second entry is x2, and here the second entry is 0. So the second entry will be x2. So therefore, this equation here holds for any x2 and x1. And therefore, we can apply the linearity again. So therefore, f of any vector x1, x2 is the same as x2 times 1, 1 plus x1 minus x2, 1, 0. And here we use f is linear. So therefore, this is x2 times f1, 1 plus x1 minus x2, f1, 0. And now we can look up the values for f1, 1 and f1, 0. So 1, 1 is the value of f1, 1 is 0, 1, 2. So this is x2 times 0, 1, 2 plus x1 minus x2, the value of f1, 0, which is 1, 1 minus 1. 1, 1 minus 1. And this we can write out. So here x2, 2x2 plus x1 minus x2, x1 minus x2, x2 minus x1. And if we write this out, we get x1 minus x2. Here we just have x1. And here we get minus x1 plus 3 x2. So here we see now, given this information here, the value of f at any other point can also be determined. Namely, it's given by this explicit formula here. And now the question is, what is the matrix of f in this case? So here it's not so easy to see from this, because the matrix of f has the values of f at e1 and e2 as the columns. But here we just have the value of f at e1. But we can read off the matrix of f here. Well, there are several ways we could determine the matrix of f. So for example, we could determine what is f of e2. So what is f of 0, 1? We use this formula. But here we can also see directly that this matrix we are looking for is given by 1, minus 1, 1, 0, minus 1, 3. Because this vector here is given by this matrix times this vector. But you can also check that this here, I mean this is f of 1, 0. This is what we already had before. And this here is f of 0, 1. And the whole thing here, this is the matrix of f in this example. Okay. And yeah, so this we will do in general later. So there's a name for vectors which satisfies this property that I can write any vector as a linear. So this is called a linear combination of these two vectors. So then we say that they generate, in this case, R2. So, but sometimes, even if I have a map here from R2 to R3, sometimes it would not be enough to just give you two values. So for example, if you give you the value of f11 and I give you the value of f22, then this would not be enough to determine the value of f at any other point, because if I take 22 here, then you will not find numbers here such that any vector can be written as some combination of 1, 1 and 2, 2, because this would be just the case if x1 equals x2. But in this case, this works, and we will later also learn the statement is that these elements form a basis of our space R2. But for now, and also for the homework, the following is more important. So in general, if I give you a map or a function f from Rn to Rm, then you will either need to decide if this map is linear or not linear. And I want to summarize here what you need to do to show that something is linear, or what you need to do to show that a map is not linear. Well, what do you need to do to check if a map, in this case this f, is linear? Well, you need to check that the definition is satisfied. So either you need to check that, maybe I can copy it here, and here it's important for all. So it's not enough to just give two examples and say, well, f of this vector plus f of this vector equals f of this vector plus f of this vector. You need to check it for all u and v and lambda in R. Or, by the theorem before, another way, which is maybe the more usual way to show that something is linear, you need to show that they exist. So here is also a big OR. So either you in some way show that this definition is satisfied, or you show that there exists a matrix A of size m times n such that f of x equals a times x. And this, of course, you need to also check for all vectors x and n in Rn. And this is usually maybe the way you want to do this, because often this definition of f is given by an explicit formula, and if you can show that this explicit formula is just given by multiplying this matrix with the vector x1 up to xn, then you're done, because we know that if you define a map by multiplying the input vector by a matrix A, then this is linear. So this will be the usual way you will show that a given function is linear. And now what do you need to do to show that something is not linear? So I cannot stress this enough, because this is a common mistake. To show that a function is not linear, it's enough to give one example, a counterexample of these two conditions. So you can show, for example, you give two explicit vectors u and v, such that f of u plus v is not the same as f of u plus f of v, or you give one explicit example of u in Rn and lambda in R with f of lambda u is not the same as as lambda times f of u. So in the homework, if you want to show that something is not linear, just give one explicit counterexample for this or for this. Even though I will say this now, I will still get submissions where people show a counterexample for this and this, but you just need to show that one of this is not satisfied, because the definition of linear is that this is satisfied, both of them are satisfied for all. So if you give one counterexample for this or this, then this is not satisfied anymore. Okay, so let's do one example here. So for example, let's consider the function f from R to R. And maybe let's also use a capital F here, which is given by sending x to e to the power of x. And first we need to think about, is this a linear map or not? And maybe your gut feeling should be that this is actually not a linear map, because maybe this doesn't look like this. But please don't just write this because e of x equals not a matrix times x. You need to show why this is not a linear map, and to show that something is not a linear map, we maybe just give one explicit counterexample such that this or this is not satisfied. And now, what can we choose in this case? We want to make our life easy, so maybe let's use the most simplest value for x, for example 0. So let's say u and v is 0. And we want to check what is f of u plus v. Well, f of u plus v is f of 0 plus f of 0, which is f of 0, which is e0, which is 1. Okay, but what is f of u plus f of v? Well, this is f of 0 plus f of 0. This is e0 plus e to the power 0. This is 1 plus 1, and this is 2. And this is not the same. And therefore f is not linear, because we give this one counterexample. So what you should not do is write e of x plus, let's say u and v. So if you write this, well, in this case, for this u and v, it's clear. But in general, this is not true, because there are some values of u and v such that this actually is the same. So do not just write the map f is not linear, because this is in general not true. To show that this is not true in general is by giving one explicit counterexample. But you can give, for example, explicit u and v such that this is actually true, and I give you one example in the lecture notes. But let's erase this. Okay, so in the homework there will be some examples of functions, and some of them are linear maps and some of them are not linear maps. And so you need to look at them and then first decide, what do I want to show? And if you think they are linear, then you should try this approach here, usually by writing down a matrix and then show that the f of x equals this matrix times this vector x, and then you're done, because functions of this type are always linear. And if it's not linear, you just give one counterexample of one of these conditions. And yeah, that's all. So next time we will talk about certain linear maps which have some nice geometric interpretations. So they will be given by some reflections or projections or rotations in space. And they will have also a lot of applications to which we come later at this course. For example, if you talk about computer graphics, then the projection will play an important role, because you want to project a 3-dimensional object to your 2-dimensional monitor. But yes, so this we will do next time. See you then.